Welcome. In this lecture I'm going to go through how to calculate some of the fluid moments, some of the fluid equations from kinetic theory. So this is a slightly more rigorous way of doing things than the heuristic argument used in some previous lectures, where we just tried to look at the flow of momentum and energy and mass around the system. In this case we're going to do a more systematic approach, where we start with the kinetic equations describing the particles and the distribution functions. And then we're going to, from those equations, derive the equations for momentum and, in this case, also density. So I'm going to introduce the kinetic equation. This is going to be a very quick overview, so if you haven't seen this before, please look it up online. Look up either Boltzmann equation or in plasmas the Vlasov equation. It's very similar. It just includes the extra electromagnetic effects. Then we're going to go through calculating moments of these equations, and then see the closure problem again, which we saw briefly in a previous lecture, but now we're going to see in how it turns up in a systematic approach. So the kinetic equation describes the distribution of particles, so how many particles have a particular position, how many particles have a particular velocity. So this is a kind of like a probability density function in a way. So kinetic. So what we have is we have a distribution function. So distribution, and this is some function of time, velocity, and space. And the important thing here is, and this can get very confusing, is this v. This is a coordinate. It's not an evolving quantity like u I've used for fluid velocity. It's something which is changing in time and space. This is a space. This is a coordinate. So it's just like x. It's something which is not changing in time. And this means you have a seven-dimensional function. So it's 7d if you include time, which typically makes this very hard to calculate. But if we just draw it in 2D, what we have here. So here we have on the velocity coordinates, say vx, and here we have the x direction. So this would correspond to solving the Boltzmann equation, say the kinetic equation along a single line in x, and you'd have the velocity in x and the position x. And what this f function says is how many particles are inside a particular box inside here. So we have a box which is size dx and dvx, and the number of particles inside this box is given by f, just right out here, so f times dx dvx is the number of particles inside that box there. So this is number inside a small region. And so every region in space, in velocity space and in real space, we can describe how many particles are in that region using this function. And then as the system evolves, particles move in space, so they move in the horizontal direction here, or they accelerate, so they move up, or slow down, so they move downwards. And the evolution of this is described by the Boltzmann equation. So we have df by dt plus v dot grad f. And so this is the motion, the advection, so the motion of particles in the horizontal direction. And because this v is a coordinate, what's happening is that at the origin here, so when vx equals 0, particles are not moving. Particles which are higher and higher up this line are moving faster, so the flow velocity is just determined by where particles are in this vertical coordinate. This is not a time evolving quantity, it's just where they are in here. Determines their flow speed, and particles are streaming. So on this, if vx would be flowing this way. So particles are streaming along the x direction depending on their vertical position. And then the other part is if you have a force So we want to have forces on the particles, so F, and then I have a mass, so ma is like the mass of the particles, and then here we have a what do we have here? So here we have a dot, and then here we're going to write this as d by dv, which may look a bit confusing, but this is just like d by dx. This is now d by dv in this direction of F. And so this means if we have forces on the particles, well, they'll move up or they'll move down. And now this is equal to the collision operator. So this is some function which we'll look at in more detail in future lectures, but this plays quite an important role. So this is the collision. This is the collision term. One interesting fact is that this is not an exact equation, although it's sometimes presented as such. This is actually already an approximation of a much larger set of equations. It's the Liouville equations. And there's something called if you're interested, the BBGKY hierarchy. Is essentially how to go from this full system, the Hamiltonians, to this essentially Boltzmann equations. So it's much more precise than the fluid equations we're going to derive, but it's already an approximation, which essentially assumes that the collisions are short compared to the time between collisions. So there's the particles are moving, then they collide, then they move again independently, then they collide again, and if that's true, then this Boltzmann approximation holds. Okay, now what we want to do is we want to calculate from this equation. We'd like to calculate equations for fluids. So fluids, we want to calculate things like the mass density, which is some function of time and space. The flow velocity, so the average flow, which again is some function of time and space. Note, unlike V, so U is now an evolving quantity, and of course things like the internal energy or the pressure, which again is a function of time and space. So to do this, what we want to do is we want to start with the density equation. So density just describes how many particles there are at each location in X. And so essentially what we're doing is we're taking a slice through, we're integrating in the vertical direction. So we're saying how many particles with any velocity are at that location. So I can draw this like this. So for example, density. So we have the same, once again here with X and Vx. And I was saying how many particles are within a small region here, like dx. We're basically integrating in Vx. So saying we don't care how many what velocity they have. We just want to know how many particles are at that location. And so you can just define the mass density, it's T and X. So it's the average mass of the particles, and then we're integrating in velocity, F, which is T, V, and X, and we're integrating that in V. So note this could be a two-dimensional or three-dimensional integral if there are multiple velocity dimensions. Here it would just be a single integral in the vertical direction. And so we integrate out this velocity dimension, and so we end up with something which is just time and space. Okay, so and this is called taking moments. So this is actually the 0th moment. So we'll see there's a more general formula which we'll see shortly, but this is the 0th moment of the Boltzmann equation. And now we want to know, having defined this, how does this quantity change in time? And so to do that, we want to know just what how the integral of f dv changes. And so we can just integrate the Boltzmann equation. So all we do is we say, I'm going to have mass, I'm going to integrate, and then I'm going to take the Boltzmann equation. So it's this. So this is just integrating that first term. So go back here and show you. So then we want to integrate this term, and for now we're going to assume that this term is 0. So later on we'll introduce things like electromagnetic forces, and then this will come in. But for now I just want to concentrate on this term and the collision terms and see how they behave. So for now we're just going to integrate this term and the collision term. So we have plus an integral of this v dot grad f, and then we're ignoring the forces for now, and so we just have the integral of c, so it's the collision term. Okay, well, so this notation, so dv, perhaps if it's not clear, so this dv is just dvx, dvy, dvz. So it looks a bit like a vector, but it's implying integration over all three velocity dimensions. Okay, so this term, so obviously the d by dt can come outside here, and so this term just becomes d rho by dt. So this first term is just d rho by dt. Okay, so this term needs a bit more manipulating to get this to work. So so this whole thing here, where we have the integral of this term, so this term can be written as the divergence of the integral of v f dv. Put them in brackets. So essentially, because this velocity here is a coordinate, it doesn't depend on x, so it doesn't depend on this derivative. So this can come straight through here. Similarly, this v doesn't depend on x, and so the whole thing can come outside. If I write this in one dimension, it might be clearer. So we have an integral of vx df by dx dvx. So this would be this thing. Now vx and vx here and vx there don't depend on space. They're just vx is just the vertical dimension, and x is the horizontal dimension, and so vx doesn't depend on x, and so this d by dx can come straight outside. So we can just write d by dx of the integral xf dvx, which is the one-dimensional version of this expression here. And so now we have this term, which is so here you have divergence of this integral vf dv. And now this is actually the flux. So this is rho u, and then the last term is this collision term. So we have so it is ma integral of c dv. Okay, so now we have essentially what looks very much like the fluid equation, so the first fluid equation we had. So we have a d rho by dt plus a divergence of rho u, which we defined as being this quantity here. So I've lost a mass somewhere here. So this should be a mass. Mass ma. So we've got a rho u here, and then we have a collision term here. Collision of f dv. And this turns out to be 0 if the distribution function is Maxwellian. So if you have a local thermodynamic equilibrium, then we get back exactly the same density equation we had before. And now you see you have a problem. We need to know what this is. So we need to work out what rho u is. Except now we can see from this derivation that rho u is defined as this, and so we can work out what the time derivative of this is by again modifying the Boltzmann equation, and now we want to multiply through by v and then integrate it. So if we do again the mass times the integral And now we multiply by v, and we get, so we have a df by dt. And I'm integrating in again through all velocity space. So this is just the first term, and now this is the first moment. So the 0th moment was v, just had a 1 here essentially, and now we have a v. In general, we'll have things like the integral of v to the n df by dt. And this will be the nth moment. So here this is the first moment, because we have v to the 1. And now we have again. Now we have a v. We have a v dot grad f dv. And we have the collision term dv. Okay. So now we have well, this is going to essentially turn into rho u, because here this d by dt will come outside, because then v doesn't depend on time. This will transform into essentially the stress tensor, which will become partly the pressure in some limits, and then this again is a collision term, but here we have a v term. Okay, so this first term, so d by dt comes through outside, and this just becomes d by dt of rho u. This second term, again we can take the gradient in space outside, and so we can just write this as the divergence of, you have again the mass, and now it's a tensor quantity, so we have two velocities, and we have an f integrated in over all velocity space. And yeah, it's the integral of this v collision term dv. Okay, so you can see the closure problem coming up again, that now we have a term involving v squared. In order to calculate this, we need a term involving the second moment of the distribution functions. This is a v squared term, and you can see this is all coming from this v dot grad f. So every time we multiply through by v, we'll add another v here, and this v will come in, and we'll always, for any moment here, we'll end up with needing the next moment. And so the nth moment depends on the n plus 1th moment. And so we need some way of stopping this infinite expansion, or infinite series. And that's the closure problem. Okay, so this term here we've ended up with a second moment of the distribution function. So this term, so if you have an so integral of v f dv. So this is essentially the flow of momentum in the lab frame. So flow of momentum in lab frame. So it's the frame that we're measuring v. So v is measured in the lab frame, and then this is the flow of momentum in that frame. So that. Okay, so we can write it in a slightly more familiar way if we change the velocity coordinates. So if we write in terms of a relative velocity, so relative velocity. So we write that w is essentially the velocity minus u, where u is the average velocity. So we move into the frame of the plasma. So that on average, the average of w is 0. So this is the fluid velocity. This is the particle velocity in the lab frame, and then this is the relative velocity. So it's the velocity of the particle relative to the fluid. And so on average, the average of w is 0, averaged over all the particles. And so we can write this term out here. So MA integral VV. So this term we can just expand out by substituting this in here. So this is MA integral, we have W plus U, and W plus U, and then F dV. So this is going to expand obviously into a few different terms. So we have here, we have MA. So the first term we have a W squared. So W term. Next we will have terms involving MA. Now we have a WU and a UW. FDV plus obviously a MA integral UW FDV. And we'll have a U squared term as well. So this term is called the pressure tensor. So this term is called P. Is the pressure tensor. So if we have a nearly Maxwellian or Maxwellian fluid, this is just a scalar and just becomes the regular pressure. If F is non-Maxwellian, then this can have additional terms, and in general is a tensor like this. These terms, now here we have essentially an integral over velocity, and here this U. So U is a function of time and space, but it's not a function of velocity, and so this term can just come straight outside, and we just have essentially an integral. So we end up with an integral of WF dV, the U coming outside, and this is equal to 0 because we've defined the average W to be 0, so because W is just the relative velocity. And finally this term here. So again we have a U which doesn't depend on space. So U depends only on time and space, but not on V. And so this term here becomes U, and then we have the integral of F dV. And this is, which is just U, and this is rho over MA. So if you multiply this by MA, you get back the mass density. Okay, so in working out this term, so the first term we keep, that's the pressure tensor, the second terms go to 0, and this last term gives us this advection kind of term. So here we have a UU and then a mass density here. So this, if we put this back into this equation, so here we have a d by dt of rho u. So we have a d by dt of rho u plus we have this term here, which you need to multiply through by ma. What's that ma here? So that can actually go there. Okay, so here we have this term. So we have a divergence of u rho. From this whole term, we take the divergence of this term plus divergence of this pressure tensor, and then on the right hand side we have the collision operator term, so collision F dV. Okay, and this looks a lot like the momentum equation. So this is a slightly more general version of the momentum equation we derived previously. So if we have Maxwellian, so if it's a uniform isotropic Maxwellian, then this divergence of P becomes divergence, so gradient of pressure, and so this term becomes the same as we derived previously for the Euler equations. This term, the advection of momentum, is the same as the Euler equations. Then this last term here, this gives the viscosities. So ma integral of v collision operator on distribution function f. So this term becomes basically viscosity. And deriving that will be a future lecture on how this is calculated. So if we have a Maxwellian distribution, we can neglect if this goes to 0. We can assume, if we assume that there's no viscosities, there's no collisions, then we get back the Euler equations. So in summary, first, if we have Maxwellian, and assume that there's no collisions in the velocity equation, so no viscosity, then we recover the Euler equations. So this just provides a more systematic way of doing it. So we have the closure problem. So that we're taking moments of the distribution functions, so we're taking moments, let's see, Vn f dv. So we're multiplying through by factors of the velocity, and this depends on the next. So every time you try and calculate how this evolves in time, you end up with an equation involving the n+1th. And so you need some way of either truncating or stopping this and closing the set of equations, so that you have a set of equations which only depends on themselves and not on an unknown higher moment. So you can do things like truncate. For example, you just say that some higher moment is equal to 0, or you can have a more systematic approach where you do some expansion in a small parameter. Or there's things like Chapman Enskog. If you're interested in looking up more details of how this is done more systematically. Okay, so this whole approach essentially ends up with a very similar equation as the Euler equations we derived heuristically before, except now we have a more systematic approach. We can now derive essentially almost mechanically from the Boltzmann equation each term in the equations, which means it's easy to go to higher moments. The maths gets much longer, so if you want to go to the pressure equation, it will take longer, and then we can go to higher moments. So the heat flux, for example, would be the one after pressure, and it gives us a way of working out essentially what these terms look like, so what the pressure term looks like, and a path forward to try and calculate them. So in future lectures I'll try and go through and show how that's done. Thank you very much.